Imagine a world where clean, efficient energy is abundant and accessible. Picture silent vehicles emitting only water vapor, homes powered by reliable, eco-friendly systems. This is the promise of fuel cells, a revolutionary technology poised to transform our energy landscape. But how long will this promise last? The longevity of fuel cells is a critical factor in their viability, shaping the future of clean energy adoption. In this exploration, we'll delve into the intricacies of fuel cell lifespans, uncovering the science, innovations, and potential they hold for a brighter tomorrow. At their core, fuel cells are elegant energy converters. They represent a sophisticated blend of chemistry and engineering, transforming chemical energy directly into electrical energy with remarkable efficiency. They function like miniature power plants, generating electricity through an electrochemical process. This process is not only efficient but also environmentally friendly, as it produces minimal pollutants compared to traditional combustion methods. Imagine two electrodes, an anode and a cathode, separated by an electrolyte membrane. This setup is crucial for the fuel cell's operation, as it facilitates the necessary reactions to generate electricity. Hydrogen fuel flows to the anode, where it's split into protons and electrons. This splitting is a fundamental step, as it sets the stage for the creation of an electrical current. The electrolyte allows only the protons to pass through to the cathode, while the electrons take a detour, creating an electrical current. This detour is what powers devices and systems connected to the fuel cell. At the cathode, these reunited particles combine with oxygen from the air, producing water as the only byproduct. This reaction is not only clean but also highlights the efficiency of fuel cells in utilizing hydrogen. This continuous process, as long as fuel is supplied, makes fuel cells a compelling alternative to traditional combustion-based technologies. They offer a steady and reliable source of power without the fluctuations associated with other renewable energy sources. Fuel cells are not a one-size-fits-all solution. They come in various types, each designed to meet specific needs and applications, making them versatile in their use. Different types of fuel cells, such as proton exchange membrane fuel cells, PMFCs, are known for their quick startup times and are often used in applications requiring rapid response. Solid oxide fuel cells, SOFCs, on the other hand, operate at higher temperatures and are suitable for stationary power generation due to their high efficiency and fuel flexibility, and molten carbonate fuel cells, MCFCs, which are also used for stationary power generation but can operate on a variety of fuels, including natural gas and biogas. These different types cater to various applications from transportation to stationary power generation. For instance, PMFCs are often used in vehicles, while SOFCs and MCFCs are more common in industrial and large-scale power generation. Each type has its own unique characteristics and lifespan considerations. Understanding these differences is crucial for selecting the right fuel cell for a specific application, ensuring optimal performance and longevity. The lifespan of a fuel cell, a critical factor in its economic viability, is influenced by a complex interplay of factors. These can be broadly categorized into three main areas: material properties, operating conditions, and maintenance practices. The materials used in constructing a fuel cell play a pivotal role in its longevity. The electrodes, electrolyte membrane, and other components are subject to degradation over time, affecting performance and ultimately lifespan. Operating conditions, including temperature, humidity, and load cycling, also significantly impact fuel cell durability. Extreme temperatures or frequent on-off cycles can accelerate wear and tear. Maintenance practices further influence fuel cell lifespan. Regular maintenance, such as system checks, cleaning, and component replacement, can mitigate degradation and extend the operational life. Section 4. Material marvels. The building blocks of longevity. The quest for durable fuel cells begins with the materials used in their construction. These materials are the foundation upon which the longevity and efficiency of fuel cells are built. Without the right materials, even the most advanced designs would fail to meet the demands of modern energy needs. Each component plays a crucial role, and advancements in material science are constantly pushing the boundaries of fuel cell longevity. From the smallest particles to the largest structures, every element must be meticulously designed and tested to ensure it can withstand the rigors of operation. The electrodes, for instance, are constantly bombarded with reactive chemical species during operation. This relentless exposure requires materials that can endure harsh conditions without compromising performance. This can lead to corrosion and degradation, reducing the efficiency of the fuel cell over time. The challenge is to find materials that not only resist these effects, but also maintain high levels of conductivity and reactivity. Researchers are exploring novel materials like platinum alloys and non-precious metal catalysts to enhance electrode durability and reduce costs. These innovations are crucial for making fuel cells more accessible and sustainable. The electrolyte membrane, responsible for conducting protons while blocking electrons, is another critical component prone to degradation. Its performance directly impacts the overall efficiency and lifespan of the fuel cell. Exposure to high temperatures, impurities in the fuel, and mechanical stresses can shorten its lifespan. These factors create a challenging environment that demands robust and resilient materials. New materials such as reinforced polymer membranes and ceramic electrolytes are being developed to improve membrane durability and extend fuel cell life. These advancements are not just about making fuel cells last longer, they are about making them more efficient, cost-effective, and viable for widespread use. The future of energy depends on these innovations, and the work being done today will pave the way for a more sustainable tomorrow. Section 5. Operational impacts. Navigating the road to long-term performance. Operating conditions are akin to the environment in which a fuel cell lives. A nurturing environment can significantly extend its lifespan, while a harsh one can lead to premature failure. Temperature extremes, both high and low, can stress the materials, accelerating degradation. Operating fuel cells within their optimal temperature range is crucial for maximizing their lifespan. Frequent start-stop cycles, common in automotive applications, can also put stress on fuel cell components, leading to faster wear and tear. Fuel purity is paramount. Impurities like carbon monoxide and sulfur can poison the catalyst, reducing its effectiveness and shortening the fuel cell's life. Maintaining a clean fuel supply is essential for long-term performance. Section 6. The maintenance mantra. Extending the life of your fuel cell. Just like any complex system, fuel cells benefit from regular care and attention. Proper maintenance can significantly extend their operational life, ensuring optimal performance and reliability. Regular system checks are crucial for identifying potential issues before they escalate into major problems. This includes monitoring fuel cell voltage, current, and temperature to detect any anomalies. Cleaning the fuel cell system periodically is essential for removing impurities that can accumulate over time and hinder performance. Component replacement, while inevitable due to wear and tear, can be strategically managed to maximize fuel cell lifespan. Replacing aging components before they fail can prevent costly downtime and extend the overall operational life of the system. Section 7. Fuel cells versus the competition, a comparative look at lifespans. How do fuel cells stack up against other energy technologies in terms of lifespan? This is a crucial question as we move towards more sustainable energy solutions. The longevity of an energy technology not only impacts its economic viability, but also its environmental footprint. While fuel cells are still a relatively young technology, advancements in materials and design have significantly improved their durability. Researchers and engineers are continuously working on enhancing the components of fuel cells, such as the membranes and catalysts, to ensure they can withstand the rigors of long-term use. In transportation, fuel cell vehicles are proving their mettle. These vehicles, powered by hydrogen, offer a clean alternative to traditional gasoline and diesel engines. They emit only water vapor, making them an environmentally friendly option. PMFCs, commonly used in cars and buses, are now achieving lifespans comparable to internal combustion engines, with some models exceeding 5,000 hours of operation. This is a significant milestone, as it means that fuel cell vehicles can now compete with conventional vehicles, not just in terms of performance, but also in terms of longevity. This translates to well over 150,000 miles of driving range, a testament to the progress made in fuel cell technology. Drivers can now enjoy the benefits of fuel cell vehicles without worrying about frequent maintenance or replacements. In stationary applications, fuel cells are demonstrating remarkable longevity. These applications include providing power to buildings, data centers, and even entire communities. The ability to operate continuously for long periods makes fuel cells an attractive option for these uses. SOFCs, known for their high efficiency and fuel flexibility, can operate for tens of thousands of hours, providing reliable power for homes and businesses for years to come. This makes them particularly useful in areas where power reliability is critical, such as hospitals and emergency services. This long lifespan makes them a compelling alternative to traditional generators, particularly in remote areas or for critical backup power. Unlike traditional generators, which often rely on fossil fuels and require regular maintenance, fuel cells offer a cleaner, more sustainable solution. They can be powered by a variety of fuels, including hydrogen, natural gas, and biogas, making them versatile and adaptable to different energy needs. As we look to the future, the potential of fuel cell technology continues to grow. With ongoing research and development, we can expect even longer lifespans and greater efficiencies. This will further solidify the role of fuel cells in our transition to a more sustainable energy landscape.